Um, Hello, everyone. Welcome to the meeting today. As you may know, since last meeting, StarRocks is our next generation sub-second MPP database, which has blazing fast speed as a killer feature. You can get most of the query result within 1 second. You can use StarRocks in real-time analytics. In this talk today, I'm gonna introduce the way of how StarRocks do real-time analytics and why we can do this so fast in StarRocks. In the rest of this meeting, I'm gonna go through each of the items below, drive you guys into the detail of StarRocks and real-time scenario. At first, let's review some real-time challenges in the world. Then I will show you StarRocks' powerful solution for those real-time requirements. You can see how StarRocks deal with real-time scenario in different way and what's inside StarRocks real-time engine. At last, I will show some demo and user case, which is from our client. Hope you can join the meeting today. Now let's get started. In the real-time world, we want to get any response just in a second. The client or internal user, they don't really care about what happened inside the system within this 1 second. So the most important challenge of the OLTP database system is related to 3 aspects. One is data freshness, which is more related to real-time data ingestion. The other one is query latency, which is more real-time queries like web UI, BI reporting, SQL query app. Those 2 aspects will both affect the end user feelings, and they affect each other as well. Another aspect is the cost of the system. Some engineer may use more CPU. Some engine may use more CPU, more memory storage for the data index or less data compaction to improve their performance, but they have to pay more for the results what they're using. The system admin cannot just scale up the cluster size to get the best result. It's a kind of trade-off decision you have to choose. It's also related to maintenance cost and learning cost as well. The next generation of the OLTP database must have a good balanced skill of that. Finally, all of the challenge above has been solved in StarRocks. I will go through each of them today. Let's have a look. The first part of the challenge, data freshness. When you want to do data analysis from a big data set, the first thing you maybe consider is the data ingestion pipeline. Your data may be already stored in different data sources like S3, HDFS, HEF, or OLTP database. It maybe include some structured data, semi-structured data, or unstructured data. Maybe you need to do some ETL job when data loading to prepare the data for the wide tables. And if you want to do real-time analytics, you may need to consider more, like how to streamly read the data from different data sources. Is there any small network interruptions or any other issue can happen? How can we still keep the data insert correctly when the issue happen? How do I rebuild the white table when anything change? Because if the real-time, if without any real-time update skill, the backfill and the white table rebuild will need time in hours. The answer here I will give you is StarRocks. StarRocks supports stream and bench data import for various data sources, guarantee the ACID transactions exactly once or not happen at all. No need for the white table anymore. That just need go each of the table directly based on your data model like Star schema or Snowflake schema. The incremental update feature will help you to do real-time partial data update naturally, and the engine will support real-time drawing perfectly when you query them. Here is an example. which is from our client Airbnb. They have a system called Minova. The Minova is the internal unified metrics platform designed with the version of our user-defined metrics once use them everywhere. The system have over 12,000 metrics and 4,000 dimensions. So it's used to build a dimension wide table before use StarRocks, and push out the metrics inside the dimension table and build a big one and deliver it to like Druid, Presto, Spark. So before they use StarRocks, this is a nightmare because if any small piece of the dimension table change, denormalize the table change, you have to refill all the data and rebuild the whole denormalized white table. So after they move to StarRocks, the StarRocks do not need to do any denormalized white table. So we can do the on-the-fly joins and provide sub-second query latency. So no need to do the pre-aggregate like Druid or Presto and handle high cardinality dimensions much better. So this is the way how Airbnb Minova use StarRocks to replace like Druid and Presto. So after that, their ETL, the whole ETL process become really simple. They just need to import the data directly to the different database and do not need to do any denormalized white table anymore. So this is the full picture of StarRocks data load architecture. As you can see, you can use Flink Kafka to import data streamly and benchly to various data source because stream load, based on the stream load, routine load, and broker load API, which provided by StarRocks. I will introduce each of them one by one later. Also, you can use the external table to query the data from data source directly without any data ingestion, which is very useful when proof of the concept. And after the proof of concept, you can use insert into select to import the data from external table to StarRocks. Here is our Streamload API. So it's HTTP based and chunk support and the basic authentication support. JSON response provide synchronize the loading and the configuration support. So here at the left bottom, you can see a CUL example, which include some of the configurations and which you can change. And also, if you want to put more, there's a document on our website. You can add more configuration in the HTTP header. The procedure happen steps is on the right side. You can see the CUL command will send to the FE node, and FE node will find out coordinator BE and finally distributed the query into different BE node. Next example is the routine load. This one is more for Kafka import. It supports SSL, support CVS and JSON, and you can use the command to show, stop, pause, and resume the whole process. At left, you can see there is an example to use the SQL to create the routine load job, which configuration is for like Kafka cluster, IP, port, max numbers, arrows, all the things you can configuration. And at the right side is the architecture to show you how StarRocks implement this task. All right. The primary key mode has better support for real-time and frequency updates. And ingestion is always a collection of upsert and delete operation. The problem is how to quickly find the latest version of the data after an upsert or delete operation occurred. The mechanism StarRocks use is delete and insert, put it in a simple way. When ingest occurs, StarRocks will find the location of all rows involved in upsert and delete operation, use the primary key index, mark them as deleted. The deleted information is recorded in a bitmap file, append the new data directly, and update the metadata at the end of the operation. And when query happens, StarRocks will quickly skip all the data marked as deleted and get the latest version of the data. In this way, we can guarantee the query speed. There's a lot of details and the designs, like how to handle the compactions, how to handle the conflicts in concurrent ingestions, how to design the primary index so it can be looked up quickly. You can find more details in our online document. The primary key mode is most suitable for real-time data updates, especially for scenario in which data needs to be synchronized from MySQL or other OLTP database to StarRocks. You don't have to denormalize the white table anymore. The primary keys account for only a small portion of the entire data, and the memory overhead is very low. After the data freshness challenge, let's have a look at the query latency challenge. This is more related to the client side. A lot of different users from internal or external will use different tools, send different queries to OLTP database. You can't even know which query will consume most resource, which query need return as soon as possible. And if combined with data upsert, high concurrency, or more complex query at the same time, your system will get really high pressure. The system must have the scalability to keep the response time still within a reasonable time range. StarRocks did a lot of optimization to face those kind of challenges. Use the partition and bucket as the double layer data sharding, which can distribute the data into a multi-node and auto-balance them using CPU and MPP database to generate and run the best query execution plan for multi-table real-time join, improve the parallel performance. Using native vectorized execution engine allows StarRocks to fully utilize the processing power of a CPU, resource group, which can control each query resource usage, while not affect others. Support multi-replica for both high concurrency and high availability. Different kind of broadcasting join will significantly reduce the distributed data transfer workload. Real-time aggregation and the intelligent materialized view can help for auto data pre-aggregation, which can improve the query latency to sub-second level and keep sync auto maintain at the background. Here's another example, which is from our client Airbnb. They try to use the Tableau dashboard to build a client report for the internal and external user. Before they using StarRocks, they tried Presto, which they got really bad performance from Presto. Each of the query average return is in a minute level, normally less than 10 minutes. So it's not a acceptable responsible time. So they have to hold on until they find the solution from StarRocks. They give us a example. This example is from their production line. They're using 3 tables, which one have 500 million rows, one have 6 billion rows, one have 100 million rows, and do this 4 joins, 3 distinct count and JSON function and registers at the same time. So they do this complex query with 3 tables and a lot of different functions at the same time. The response time is just a 3.6 seconds. So this is a real-time multi-table join in real world, in real production in Airbnb. So in this kind of response time, they will have availability to implement this kind of product for the users, like the data science team, the AI team, and the client as well. So StarRocks use partitioning followed by bucketing to support two types of data distribution, range distribution and hash distribution. In real-world scenario, the timeline of the data is important. New partitions need to be created and expired partitions need to be deleted. StarRocks dynamically partitioning mechanism enables partition rollover, can provide time to life, TTL management to automatically add or delete partitions. StarRocks use the hash algorithm as a bucketing algorithm within the same partition that with the same bucket key form tablets. Tablets replica are physically managed by separate local storage engine. Data import and query take place in tablet replicas. Tablets are the basic unit of data balancing and recovery. So it's the basic unit of the StarRocks storage. So this one is the to show you how we can do the multi-table join in real time so fast. It's because StarRocks can do different kind of distributed data join across different storage nodes. StarRocks will optimize the join tab based on the data statistics. Shuffle join will hash the data to specific node rather than do a full network broadcasting. It will significantly reduce the data network transfer size and save more time. The co-locate join will utilize the local data replica to avoid any network data transfer, only do the data join locally. It's really useful when you do some large table join. Those kind of distributed data join is helping us to help customers to restructure their data import pipeline. No need to do any denormalized white table anymore. The data import and ETL process becomes super simple because of the real-time multi-table join. The native vectorized execution engine allows StarRocks to fully utilize the processing power of CPU. Most specifically, native vectorized execution support column-oriented data management and processing. As a result, this kind of engine allows StarRocks store data, organize in memory data, and runs SQL operators by columns. In this way, column-oriented data management make effective use of CPU cache. It creates fewer virtual functions and the selection statements, which will improve the efficiency of the pipeline in the CPU. On the other hand, the native vectorized engine make full use of SIMD instructions in the CPU to allow StarRocks to function with fewer instructions. It's confirmed by standard benchmark testing that StarRocks native vectorized engine can improve the overall performance by 3 to 10 times when implementing operators. The vectorized engine provides StarRocks with the technology of operation on encoded data when implementing operators. StarRocks can implement operators on encoded string without decoding, such as the join operator, aggregate operator, and the expression operator. This can greatly reduce the complexity of SQL computation, the SQL computing during the execution, and increase the query speed by more than 2 times. In multi-table join query, in addition to execution engine, optimize the execution plan can also play as an essential role when improving the query performance. Because of the cost between the best plan and the random choice could be in orders of magnitude difference. The more tables in multi-table join use, the more execution plan CPU engine will generate. As a result, it's an NP-hard problem for CPU engine to choose the optimal execution plan. Only the excellent CPU engine can select the relatively optimal query plan to achieve the ultimate performance in multi-table analysis. StarRocks has designed and implemented a brand new cost-based optimizer, which is the CPU from scratch. The kind of optimizer is similar to Cascades. It's customized according to StarRocks' full vectorized engine and has made several improvements and innovations. The optimizer helps to reuse CTE, rewrite subquery, perform lateral join, support join or reorder, select a distributed query plan and for multi-joins, and build dictionaries to convert low cardinality string columns to integer columns. At present, the CBO is able to optimize a set of 99 queries in the TPC-DS testing. This new CBO engine allows StarRocks to fully exploit the advantage of the native vectorized engine. Compared with other similar OLTP database, the StarRocks has more excellent performance in multi-table join queries, especially in the complex queries. Okay, next. Intelligent materialized view provided by StarRocks can generate pre-aggregated table to speed up the aggregate queries. StarRocks provide real-time materialized views compared with non-real-time one, which need to be refreshed manually in other OLTP database. StarRocks real-time materialized view are automatically updated with the changes which made to the base table. Also, StarRocks automatically select a suitable materialized view to accelerate queries. When StarRocks conduct the query planning, it will rewrite queries to fetch results from appropriate materialized view in order to increase the speed of the query. StarRocks materialized view can be created and deleted flexibly. Users don't need to build materialized view when they create a table. You can choose whatever you create or not based on your cost-effective consideration. And then after the base table are created, also StarRocks will automatically optimize the materialized view in background. Here's another challenge, which is maybe more important than the two before. It's the cost. The cost challenge. All the numbers here is given by our clients, the real world clients, and it's significant. If you use StarRocks, it can significantly reduce the cost, about 50 to 80%. Because we're using column storage, so it's more efficient for the data compaction and save more storage space. Because we use the high performance design, so it's less computing resource use, save more CPU. Because of single system for all, not really on other third-party component, no data redundancy, so the learning cost is pretty low. Because of the easy infrastructure and easy to use, so the maintain cost is pretty low. Because no need to rely on the large flat tables, good support for the star schema and the snowflake schema, so the modeling costs are greatly reduced. The development time reduced from 2 weeks to just half a day. The above information are all come from our real customer feedback. Okay, so now this is the demo time. In today's demo, I'm gonna show 2 demo for you. One is I'm using Kafka to import some log data into StarRocks in real time and display in the Tableau dashboard in real time. Another example is the we use Flink to consume the MySQL bin log and real-time import into StarRocks based on the Streamload API, and I will display the data in real time as well. So now let's have a look at the first demo. I first use the shell application generate the logs and push to Kafka cluster. The Kafka message queue will be pulled from Spark. The Spark will do a little bit ETL process and use the Streamload API, import the data in real time to StarRocks, and the Tableau dashboard will keep a live connection between the StarRocks and Tableau and show the dashboard. So here at the bottom is the left is the database structure, the table structure. The set column is the URL. I put an example on the right side. You can see set is the URL, and the date is the date of the day, and the hour minute is hour and minute. So UV is a bitmap column. We use the bitmap unit function to optimize. It's in the original data is user ID, which is another kind of int. And after we create this table, because it's an aggregation data modeling table, so it will automatically aggregate the UV based on the bitmap function. And also you can see some configuration like the bucket, hash key, and some properties as well. At the right side, you can see the original data example, the UID, the site, and the time. Time is a timestamp. What I did in the Spark program is just load the time from the JSON data and use the datetime format to convert the timestamp to date, hour, minute in string. So and then I will call the Streamload API, upload the result into the StarRocks. I also use the materialize view, create another materialize. It's called PV. So when you do different SQL queries, it will go to different table. The first one will go to the PV materialized view, and the second one, it will go to the original table. So now let's go to the command line. Here's my command line. You can see there's a shell script that I will run. This shell script will generate the logs, and which is the JSON format by UID, set URL, and the timestamp, and insert into the Kafka message queue every 2 seconds. And here is another command I run for start our Spark application. The Spark application will read, will pull the data from Kafka message queue in real time and do the ETL jobs, convert the timestamp into date, hour, and minute string, and call the Streamload API and insert the data back into StarRocks in real time. So as you can see here, it's already started consuming the data. Now let's go to the Tableau dashboard. Here you can see the Tableau dashboard. You can configure the connections, like which database you're using and which IP and port, because StarRocks support JDBC and MySQL protocol perfectly. So we're using JDBC MySQL here. And also you can change your SQL query as a customer SQL query. So you can, at here, we just select the date, hour, minute, site, and count the distinct count of the UV, which is the bitmap column. And also group by the site, date, and hour, minute. So you can change your query here to see different results. Also, here is another some previews of the data at the bottom. So we just need to refresh, and you will see some preview of the data and also the column structures. Then you can go to the sheet tab, and you can see we use the daytime, the daytime I create is kind of string connector all the hour, minute, and date. So this is a kind of concat string, and the site is the URL access. The site URL, which you can see at the right side, there's the 3 colors refer to 3 different URL, 3 different kind of URL. So, and also I display the set URL in each of the column you can see in 3 different colors. So after this configuration, you will be able to see what is the date time and what's the number of the queries, what's the number of the real-time ingestions into the StarRocks. So this is one of my demo. Let's back to the slide. So in this demo, I displayed a way to do the data ingestion in real time from shell log script to Kafka to Spark and to StarRocks, and finally display in Tableau. Another example here, I will use my Python script, my Python application to upload some stock price data into MySQL database. The MySQL database table schema is like this. I just to show here. It's include 4 different tables, and as a schema is here, and it's a kind of real-time stock price data analysis. So after insert the data into MySQL, we use StarRocks management migrate tools to generate the table in SQL and replay in StarRocks. So after this StarRocks migrate tools run, we can get the same structures in database structures and table structures in StarRocks. And after that, the Flink CDC will consume the MySQL bin log and use the Flink job to with the Flink connector, StarRocks connector insert into StarRocks database. So this you can use the normal JDBC to insert the data, but the Flink connector from StarRocks will use the stream load, which will increase the injection performance. And finally, I will use a Python UI to dynamically show the real-time result from this ingestion pipeline. Also, I built a bit more complex query here, which join 3 different tables and display the result in the Python UI. Okay, now let's go back to the command line. Yeah, here's the command line. Let's get start from the data injection first. As you can see, when I run this Python script, it will inject insert the stock price into our MySQL database. And here is our display Python UI. As you can see, it's running complex query and get the result every second, which ingest into the MySQL and use the Flink CDC and the Flink connector sync the data into StarRocks in real time. So this example, as you can see, it's kind of real-time ingestion from the OLTP database to StarRocks. This use case is another one from Airbnb. So they have a real-time trust analysis system to do the fraud detection, the attack detection, and their data science team use ad hoc queries and real-time updates to do the real-time analysis. They will make different rules to query the data side to figure out if there is any new kind of attack or find some static report for the team. So in this solution, StarRocks using primary key to provide the real-time update because all the transactions, all the data they import need to update and show to the data science team in real time, and so they can find and trigger the rules immediately. So that will help Airbnb to save to keep safe of their system, to make their fraud detection system really strong. And data import from Kafka in sub-minute delay, and StarRocks provides second level query latency for the complex join query. As I showed you before, three large table and a lot of different functions triggered in same time, just the 3.6 response time. So they can alert these kind of attacks or detection result in real time by just running some SQL query regularly. So, okay, thank you for your time today. It's question time now. If you have any questions, please let me know.
Alrighty, hey Peter, we do have a question in the chat window.
Yeah.
I think gentleman Vinayak asked the two part of the question, or two questions. First one is, does delete insert strategy provide good performance when millions of records are received from source?
Yeah, of course. As you can see, the example from Airbnb or from our ERP clients, they do millions of the data import in real time. Yeah.
Great. And also, I think Chelsea also added some explanations to the primary key index in chat box, and she listed several scenarios that best suited for this strategy.
Yeah,
I'm not going to read through this, but feel free to take a look.
Yeah.
The second part of the question was, in what formats data can be stored on DataRocks DB?
You mean the import data format or the storage format inside the StarRocks?
I think Heng, one of our community members, answered this in chat. I'll just read it out so that we can the customer have that.
I saw that. Yeah.
Right.
Storage in columnar storage format, and a bitmap indicate which row is deleted. Yeah.
Right. Great. Thank you. Another question was sent to me directly, so I pasted them into the chat window so everyone can see it. What ETL or ELT tools are most commonly used to load data into StarRocks? Can you talk to that?
Oh yeah. The ETL tool, normally you can use Flink. You can write yourself model application to run in Flink, and also you can use Spark. In my demo, I use Flink and Spark as two of them. Also you can choose another language you like, Python or other language. You can choose different.
Great. I think that's all the questions we have so far.
We also for the ETL one, yesterday we have a meeting of the team. We also developing some new kind of tools, like based on the DBT. We still keep working on different different connectors, different kind of ETL tools in our community, and you can find in our GitHub website as well.
Okay, great. Another one was how to compare Pinot and StarRocks.
Pinot is an excellent. It's an excellent open source database, I think, but it's not support the standard, the NC SQL. Doesn't support for the multi-table join. So it's not easy to use. You have to use another query engine such as Presto. So it will related to different relay on different system, cannot running just by itself. So it will bring more operation and maintain cost accordingly. So also we did some comparison with the Presto on complex query like TBCH. Our speed is much better than theirs. Even if the data is not ingested into StarRocks, the performance is 3 times better. So you can take a look at our YouTube channel to see our webinar videos and see the benchmark, and also you can like Google search the TPCH and SSB testing benchmark testing result from online based on Pinot, based on Presto and StarRocks. Yeah.
Okay, thank you, Peter. I think one more. Do we have community version of StarRocks so I can test, install, and test it? Peter, you want to talk about that?
You mean the free version, open source version?
Right. Yeah.
Yeah. Yeah, we have one. You can find from GitHub and download the source code, compile them by yourself, or you can download the already packaged the existing one from our website. We also have the docs.starrocks.com, which is our document website. You can see step-by-step document to help you to install and testing the whole environment. Yeah.
Great. Yeah. And while you are on our GitHub page, please don't forget to give us a star. So.
Yeah. Thank you.
Another question: would any ETL tool that supports MySQL work to load data into StarRocks?
Yes, of course. The demo I show you here. Let me show you again. Yeah. The second demo I show you here is using the Flink CDC connector and the Flink StarRocks connector, which is combined inside a Flink job to consume the MySQL bin log, which will, the MySQL strategy is when you insert some or update some, all the actions, all the operations will write into the bin log first. So consume the bin log, you will get the full data action, full data operation replay, and from the MySQL to StarRocks. Yeah.
Great. And in the chat window, we have pasted the link to our community or download location to download the StarRocks software, and also a video to our benchmark results and tools we use to run benchmark testings. So we will send this to all the attendees as well. I think that's all the questions for now.
Yeah. All right.
Yep. So hold on, one more message. You're welcome, Chris.
Yeah.
So if there's no other question, thank you, Peter, for the great presentation, and thank you everyone for joining today's webinar. As I mentioned earlier, we will send a survey. Please take a moment to fill out the survey. Let us know what we can do better next time. And thank you very much. Have a good day or good night, and we'll see you in the future.
Thank you, guys.